Let me introduce our speaker today. We have Dr. Kevin McCormack. He is a Stanford-educated geophysicist who specializes in induced seismicity and confined systems. Sorry. He acquired his bachelor's degree at the University of Utah and moved to Stanford for his PhD. Upon completion of his graduate studies, he moved back to the University of Utah, where he is now employed as a research scientist in the Energy and Geoscience Institute. His research focuses on forecasting induced seismicity for injection operations and using changes in the pore structure of rocks to assess physical and chemical changes. Thank you so much for accepting my invitation, Kevin, and floor is yours. Thank you so much.
All right, thank you, Sharzad. Let me share my screen. So let's go there and there, and let's make this a little smaller. All right. So my name is Kevin McCormack. As Sharzad just said, I'm a research scientist at the University of Utah, specifically the Energy and Geoscience Institute. And today I'm going to be presenting on stresses and seismicity. More specifically, what is the interplay between stresses and seismicity? And specifically, we'll be looking at creep and induced seismicity forecasting. So this is a Future Leaders seminar. This is a Future Leaders seminar. And so I thought I'd give a little background on myself. Sharzad just went over this, so it's a little repetitive, so I apologize. But I was at the University of Utah for my bachelor's. I went to Stanford where I did my graduate studies. And then I came back to the University of Utah where I'm now happily a research scientist, studying the things that I like to study. And so let's start with an overview of what the talk will look like. So we'll start with a brief introduction, and then we will look into probabilistic hazard prediction, which is where we'll be seeing how can we assess the likelihood of events, seismic events, in injection scenarios, injection parameters. And then we also have a fault curvature section where we look at what is the hazard on a curved fault rather than just like a planar fault. Does that make a difference? Does it not? And then we'll look at the creep. So this is viscoelastic stress relaxation, these rocks deforming over geologic time. How does that change the stresses? What does this change in stress have to do with the earthquakes that we observe? And then finally, we'll conclude with an Mmax prediction, which is a study looking at the maximum magnitude event that might occur during injection at two different operations. One is an EOR CO2 sequestration site, and the other is a enhanced geothermal stimulation. So let's start with a brief introduction. So as we all know, if you inject fluid into the subsurface, you pressurize the formation. You increase the pore pressure in the formation, and that it changes the fluid pressure, and then it also has a stress perturbation that changes the stresses immediately around in a poroelastic sense. And now these two factors combined, or at least the pore pressure, can cause faults to slip if they're properly oriented in the stress state and in the right location. And so if these faults slip, they can cause seismic waves to radiate out, and these seismic waves can interfere with infrastructure and cities and urban areas. And this is something we want to avoid. We do not want these large-scale ruptures shaking buildings, causing damage to infrastructure. We really do not want that, because really what all geoenergy activities rely on is the social license to continue operating. If the public says, hey, we don't want you to inject anything anymore, well, they'll probably get what they want. So let's look at the mechanism by which the seismicity occurs. So the primary mechanism by which the seismicity occurs is the pressurization of a fault plane. So that pore pressure, that elevated pore pressure from the injection, gets into the fault plane, and it supports some of the normal stress acting on the fault. And so the effective normal stress decreases. The fluid does not support any of the shear stress because fluids can't support shear. And so you have a change in the stress state from an initial stress state, which is further from failure, that decreases in the effective normal stress, and you see that it can come closer to failure. That's the primary mechanism by which these earthquakes happen, but not the only mechanism. There are also the mechanical effects, which I mentioned earlier, that zone of stress that propagates around the injection area. And then there are also thermal effects. So you imagine if you inject a fluid that's at room temperature at the surface down to a depth in the earth, the fluid's much colder. And so there's kind of like a thermal shocking that takes place. And so when that happens, you can have a perturbation of the stresses in the region, and that can also lead to seismicity. And then a third mechanism that has been observed is Coulomb stress transfer, where if you have one fault slip, the stresses in the area around that fault get perturbed, and so that can cause other faults in nearby to slip. And so that's another mechanism by which you can induce seismicity. Now, all of these analyses are pretty well understood. So Otto Moore in 1890 developed the Moore circle, and we know what the Coulomb failure function is. It's a function of the shear stress, the normal stress, and the coefficient of friction. And it's essentially a means of measuring the distance from a point, a fault in this Moore circle to the failure envelope. And so this is well understood. This has been well understood for more than 100 years. And so what we're going to do in this talk is look at very, very detailed aspects of this situation to determine what can we learn further about the mechanisms and the hazards associated with induced seismicity. So one thing that we'll look at is probabilistic geomechanics. So we'll vary input parameters in a Monte Carlo sense to look at the way that the hazard prediction varies based on the probability of different scenarios and the sensitivity of the mechanism to different input parameters. Another thing we'll look at is the curvature of the fault, which is going to take, instead of a single point for that pole, that representation of the fault orientation, will have a distribution of the fault orientation in this Moore circle space. And so we'll look at the repercussions of that. We'll look at the creep. We'll look at what happens if one of the stresses, or two of the stresses actually, become more isotropic, or all of the stresses become more isotropic. And so that's one thing we'll look at. And then a fourth thing we'll look at is so if you have many faults that are all relatively close to failure and they're going to slip, which one's going to host the largest earthquake? And so those are the four things we'll be looking at in this talk. And buckle up, we're going into probabilistic hazard prediction. So this study came from the San Juan Basin carbon safe study project, which is a carbon sequestration feasibility test in the San Juan Basin of New Mexico. So this is a little schematic of New Mexico. The San Juan Basin is up here in New Mexico. And it intends to store 6 to 7 million tons per year over 12 to 20 years. So this is a large project, and they're even proposing more funding to incorporate even more power plants, even more sequestration sites, and make it a big storage hub. And so it's a large scale project. And so we're curious what the seismicity might be. And just as a note, they're applying for a Class 6 UIC permit right now, which is a regulatory system for injection of carbon dioxide. And it's a very detailed analysis of what you intend to do and what are the environmental repercussions of that, some of which are indeed the induced seismicity. So one thing that's good to do in a project like this is to look at the past seismicity. So you see here, this is the study region. This is where they're going to inject the carbon dioxide. And there's a few earthquakes around the region. They're low magnitude events. And you can see the boundary of the basin in red. You can see the receivers that gather the data in these green triangles. And one thing I'll point out is this hogback monocline, which is essentially folded strata that bound the northern portion of the basin, or at least mostly bound the northern portion of the basin. And so keep in mind that this hogback strata, or this hogback monocline, is something that we need to be cognizant of as we go forward. So the one thing I'll point out is that the seismicity in this region is sparse and low magnitude, and seismicity in the center of the basin, where other injection is being speculated is basically non-existent due to the fact that the seismicity concentrates on the more complicated geology of the periphery of the basin. So what we need to do a probabilistic geomechanics analysis is input parameters. We need data. And so one thing we have is stress data. So you see the two horizontal principal stresses in the green and the red. You see the vertical stress in black, frictional equilibrium in blue, and pore pressure in blue. And so this is data that was obtained through extended Eaton's method. I know it's not the ideal way of getting this kind of data, but it's what we have. And then also we need the faults. We need to know we need to have some idea of what faults are present to do an analysis on each fault. And so we went through the literature and seismic data, and we formulated about 5 faulting scenarios that just encompass different aspects of where people have seen faults previously in this study area. And then the one I'll point out is this hogback flexural faulting area, which is a bunch of sub-parallel strata that have been folded, and the competent strata sort of slip past each other as they get folded, and so they create discontinuities in between the formations. And so these faults are going to be of interest in a moment, actually right now. So the only faulting scenario, so we ran our probabilistic geomechanics. We varied the input parameters using known inferred distributions of what we think the ranges and the standard deviations and the means of each parameter is. And so we were able to run 20,000 scenarios for each of the faulting scenarios. And the only one that's of interest, or well, of risk, is the hogback flexural faulting. But we're aware of some saltwater disposal injection that's directly into the same formation as the proposed CO2 injection, and it's more than 20 million tons over, or 20 million barrels over, I think it's about 15 years. And so it's a large amount of injection, and we only saw those few earthquakes. And so what we think is going on is that although these faults are geomechanically unstable, they tend to host smaller distributed seismicity across the series of faults, rather than just a single fault plane rupturing in a large fault. So we think that despite the geomechanical instability, it's reasonably good. It's reasonably low risk injection. So, and then the other thing that we can look at is the sensitivity of the input parameters. So you can see that that some parameters like the strike and the least principal stress don't really matter much, and that's because of the two horizontal principal stresses are so close together. We're in a radial normal faulting environment, and so the orientation of the SH max orientation, the orientation of the strike is not very prevalent. Now the dip you see is very big in a lot of these scenarios, and that's because the dip is very poorly constrained, so we had to use very big distributions for the dip to encompass all of the possibilities, and so therefore it becomes a very sensitive parameter in the calculations. So a summary of this section: the inputs of stresses and orientation are required. The injection appears to be safe, but for the flexural faults. But given the saltwater disposal, the geologic framework, and we believe that the hazard is not all that significant. So moving on to the fault curvature. So in this section, we're going to look at some observations. We're going to ask a question in this section. And the question is, if we discretize a fault surface, if we allow a fault surface to have more character to it, will it change these sorts of hazard predictions? And so what we'll look at first is that in many previous studies, faults are speculated to be, or modeled, not speculated, modeled to be planar systems. They're just planar faults, and each plane is assessed in its individual self. Now, conversely, we know that faults have roughness. The rocks have roughness to them. We just know that. We know that they undulate, that they have rugosity. And we also know that they curve. In space, they can curve, which is something we want to look into. And we're fortunate here because we have those hogback flexural faults, which are themselves curved faults. They're listric. They're not growth faults, but they're listric. And so these curved faults can be represented in a point cloud. So this is a representation of a fault in a point cloud based on data from geologic inference in the hogback monocline, the hogback flexural faults. And so we analyzed these data and we looked at three different ways of, or three different styles of discretization. And so we chose the close packed hexagonal spherical regions. Basically what we're doing is we're taking a mesh of close packed, hexagonally close packed spheres, and we're looking at the data that falls into each of those regions. And when those data fall into, when enough of those data fall into one of those regions, we do Bayes' law to determine what the distribution of strikes and dips might be of the data in that region. And then we have each of those regions. And so that creates a fault, a discretized fault surface. Now, this is a Bayes diagram of that analysis. And so what we do is we start with the fault locations, and then we do Bayes' law going up this way in inversion to get the distribution of strikes and dips. And then we take those strikes and dips and we input them along with the input parameters from the previous study, those geomechanical input parameters where we did the probabilistic geomechanics, and we put that into a geomechanical model, and we create a Coulomb failure function, or at least a distribution of Coulomb failure functions for each one of those regions. And now we did this with three different types of, three different radii of those spheres to try different levels of discretization. And then we also did it with a kriging. So you use all of the data in every data point, which actually worked better. So what this really ends up showing us is that the distributions of the Coulomb failure functions don't change very much, but we do get an assessment of what this hazard is in space. So this is the three radii of the discretization, and you can see it highlights a certain region in space of higher hazard. And indeed, this is the kriging, which highlights certain regions of higher hazard as well. And so we get a spatial understanding of what the data is. Sorry, people walking in the hall. A spatial understanding of what the Coulomb failure function is as a function of position along the fault. So we know that if we know curvature in the fault, we know that the kriging can produce a better understanding of the spatial distribution. It's not only the orientation of the fault that affects this analysis. It's also a matter of the stresses also change with depth, especially depth, because you can imagine going through different stress layering scenarios. And if you have data on that, you can analyze faults based on changes in the stress layering as well. And it's not applicable in all situations. I think in most situations, you're okay to just use a planar fault. But in some situations, you can actually, especially if you have a curved fault or a lot of stress layering, you can actually improve your hazard analysis. So we are moving on now to the creep section. And so the creep section is going to be looking at how rocks deform over geologic time. And so I'll first take you to the Niobrara, or the Denver-Julesburg Basin, which has the Niobrara Formation in it, in northeastern Colorado. And so this is a study I did, and there were three wells in the study. One was in the Niobrara A, one was in the Niobrara C, and the third was in the Codell sandstone, all three of which had to be hydraulically fractured and to produce the hydrocarbons contained within. And so this formation was deposited during the Western Interior Seaway during the Cretaceous. There are three wells in the study, as I just mentioned, and the SH max orientation is roughly north-south in the region we are interested in. And again, we are in sort of northeastern Colorado right there. So when they did the hydraulic fracturing, they did it in all three wells, and you can see that they created this cloud of microseismicity. And if you just look at it from the plane view, like we're doing right now, it's not very illustrative. There's not a whole lot you can see. You can see that the dark blue sort of congregates around the Niobrara A, the teal congregates around the Codell sandstone. The red congregates around the Niobrara Sea, but that's not terribly interesting. But if we go to a cross-section view, and now we look at the stresses, so I'll tell you how we get this SH-min estimate in a moment. But if we look at this SH-min estimate, and then we look to it relative to the cross-section of the seismicity, we're going to see something relatively interesting. So if we look at a histogram of the seismicity, you see that most of the seismicity, actually the large portion of the seismicity, is in the Niobrara A, and very little is in the Niobrara C. Now, if we look at the stresses in these formations, these stresses are the SH-min is lower in the Niobrara A, and it's higher in the Niobrara Sea. And so it makes sense that the seismicity would concentrate into the region where you have to perturb the system less to create an earthquake, because the stresses are closer to that frictional line. And so one aside is that a consequence of this is that if you look at the stimulation by well, so if you look at the earthquakes that occur during the stimulation of each well, you have more stimulation occurring in the Niobrara A than in the Niobrara C. However, if you look at the stimulation by formation, there's much more stimulation in the Niobrara A than the Niobrara C, which is just further evidence of the concentration of seismicity in the Niobrara A. Now, there was also more production, both in terms of oil and gas in the Niobrara A than the Niobrara C. And that could be, it's just a possibility, but it could be due to greater level of stimulation from that Niobrara, from that lower stress in the Niobrara A. Now, let's look at how we obtained that curve, that SH-min estimate. So it's using creep. You might be able to predict it's using creep. And so what we see with creep is that over time, if you apply a constant load, the strain deforms in kind of a fractal matter. It doesn't approach an asymptote, and it doesn't approach a constant. It's a fractal distribution of the strain. And so we also notice that the amount of strain that takes place, like this Haynesville 1 versus Haynesville 2, is largely related to the clay and TOC content. So the clay and the TOC are sort of the chewy components of the rock. They're the more ductile components of the rock. And if you have a lot of them, they allow for more of this viscous and elastic creep to happen. And so in the laboratory, what we do, as I just showed, is we keep a constant stress and we let the strain change over time. Now in the earth, we do the opposite, because you imagine the rocks are emplaced in the basin and they cannot strain in the basin. And so instead what happens is the stress relaxes. And now you might think, okay, if the stress relaxes, all of the stresses become smaller. But that's not really true. The stresses are becoming more isotropic. That's what we mean by relaxing. And so if the SH-min is the least horizontal, if the SH-min is the least principal stress, then that means that the SH-min is actually going to increase as viscoelastic stress relaxation happens. And so we can use this to understand, just using mathematical modeling, to understand how the stresses might evolve over time as these deformation of this small scale deformation occurs within the formations. So this is what I did to get that SH-min estimate that was so illustrative in demonstrating where the seismicity occurred. What I did was I took an equation from Monzo back 2020, and so this equation shows that the SH-min can be a function of the vertical stress minus a viscoelastic parameter. And so the components of the viscoelastic parameter are the strain since diagenesis. This is how much strain has taken place since the formation of the rock, since this process started. And then the horizontal Young's modulus, we all know what that is. It's essentially just the stiffness in the horizontal direction. And then T is the time that this process has been taking place. So in the case of the Niobrara, I think it's Cretaceous. So it must be like 80. I'm not a geologist. I think it's like 80 or 90 million years or something. So that's kind of the time frame we're talking about. And then N is the viscous parameter. N is the decay parameter. And this is a measure of how viscous the rocks are. So if we look at the horizontal Young's modulus, we can break it down into components of the stiffness tensor. Now it looks like a bit of a mess, and it is, and it's going to get even worse when I push this button. But we can see that the components of the stiffness tensor are themselves components of the velocity model and the density. And so we have the density just from logs, and the velocity model we've obtained through the seismic surveys, the passive seismic surveys. And so we have this information, and we can calculate horizontal Young's modulus. Now, once we have the horizontal Young's modulus, we can take we can use a correlation from Monzo back 2020 of the horizontal Young's modulus and the n, this viscous parameter. And so this correlation gives us a sense of the relation between the viscous component of the phenomenon and the elastic component of the phenomenon. And so we have a calculation for n. Now we take SV from logs. This is very straightforward. We have our density logs, we integrate them, no big deal. T is the time since diagenesis, so don't ask me, ask a geologist to see how long ago the Cretaceous was. And then SH min is from defits. So we take we had 3 defits. Actually, we may have had five defits in this study. May have been 5. So we had a bunch of defects in the study. We calculated we set SH min equal to those defects, and then we calculated what this epsilon naught had to be to make all of that make sense. So now we have a value for epsilon naught, and we assume that this epsilon naught is constant throughout the basin because the basin is not changing in size. And so then we relax the constraint on SH min, and now we have a now we can calculate the SH min based on what the vertical stress is and based on any point in any depth, based on how the vertical stress changes. This is constant, these are constant, and the horizontal Young's modulus changes with depth. I'm not sure I said that quite right, but I do hope you forgive me. So that's how we got that SH min estimate that was so helpful in describing the seismicity. And now we're going to transition from the Denver-Julesburg Basin to the Paradox Basin in Utah. And the Paradox Basin is interesting because it's this big basin right here that contains an enormous quantity of emplaced oil. There's a lot of oil in this basin, but it has yet to be satisfactorily produced. And so the point of this project is to understand how we can better produce from this basin. And we see that so our contribution to this is better understanding the stress state. How is the state of stress changing? And so we'll use viscoelastic stress relaxation to understand that stress state. So we have core in this study. We have about 100 feet of core, and you can see there are certain regions where the core was removed and contained in wax so as to do geomechanical testing. And you can see also that there's a lot of salt in this basin. One of the reasons why this basin is so hard to produce from is all of these salts. And so we see both of these in this picture of the core. And then also I'll point out that the fracture density in the core is a lot higher in the upper portion of the core than the lower portion of the core. That'll be important in just a moment as I relate the stresses to the seismicity. So previously we needed to use those components of the stiffness tensor to get the horizontal Young's modulus. Now we have laboratory testing. We have static laboratory Young's modulus testing, which is probably more robust. I haven't done a careful uncertainty analysis of the two, but I would imagine this is more robust. And so instead of having a constant value in depth as we had previously with those components of the stiffness tensor, we're going to instead have individual discrete points where we have those laboratory tests. Now, the laboratory tests are performed through triaxial experiments and creep experiments. So the creep experiments are really nice because you can actually disentangle that correlation, the correlation between the viscous parameter and the elastic parameter can actually be disentangled because you can calculate the elastic parameter and the viscous parameter separately from this curve in stress time space. And so when you do that, you have an independent measure of the viscous component and an independent measure of the elastic component, which is actually it's sort of more theoretically sound to do it that way, rather than rely on rather than rely on a correlation. So it's actually a really good thing. And so what these data look like when we plot them up, we do the test, we do the same kind of analysis that I showed you previously in the Niobrara, and we get discrete measurements of the SH min based on the triaxial tests and based on the creep test, the creep test that I was just so laudatory about. And so, and this is right here is the DFID measurement, and the blue dot is the DFID analysis. So you can see that the stresses are very isotropic, or at least the least horizontal principal stress is very close to the vertical stress. And also you can see that the stresses become less isotropic, that is more separation between the two, when you get higher in the core. So the Cane Creek, that's the formation we're in right now. The Cane Creek has a very high pore pressure. The pore pressure is 0.97 psi per foot. That's according to the DFID. And so that is more than double hydrostatic. So if you imagine what the stresses look like when you have hydrostatic pore pressure versus the Cane Creek pore pressure, it's a very different amount of allowable stresses. So we saw previously that the minimum horizontal principal stress and the vertical stress were very close together. However, it's also reasonable to assume that the SH max, the maximum horizontal principal stress, is also close to those two values. So we have a very isotropic and lithostatic stress state. And so the last thing I'm going to point out is that, as we saw before, the fracture density is higher in the upper portion, where the stresses are more anisotropic. And so that means it's closer to failure frictional equilibrium, easier to induce seismicity. And so perhaps these fractures that we see are related to the stress state, perhaps. So a summary of the creep section. So stresses can relax over geologic time, especially in clay-rich and TOC-rich rocks. Mathematical models can predict the least horizontal principal stress based on field data, and the seismicity can reflect these variations in the stress field. So that was the creep section. Take a break, take a sip of coffee. All right, so let's go to the last section, which is the Mmax prediction. And so here we're going to be looking at the maximum of allowable earthquake that might occur. So as we saw before, you inject the fluid in, you get stresses, you get pore pressure, you get slip. We do not want to slip, at least not large slip. I mean, I guess slip is pretty good in hydraulic fracturing settings, so long as it's contained and small. But so we want to avoid these large slips. So we want to know what is the maximum event that might occur. And so we're going to look at enhanced geothermal and geologic carbon storage in this section. So these predictions are based on physics. So these models, there are a couple of these models. There's the uncalibrated moment cap, there's the calibrated moment cap, there's the statistical, and there's the residual. All of them are based on this delta V term, which is the cumulative volume of injection. And so this cumulative injection volume as a function of time changes, and you see that the Mmax prediction also changes. And so what happens if you plot these models is that so time is on the x-axis and the maximum magnitude is on the y-axis, and these models 1, 2, 4, 3, 1, 2, 4, 3, these models all they give these curves that bound where we expect the maximum magnitude to be. Now you can see that this model, the uncalibrated moment cap, is way too over predicting. It over predicts the data significantly. And sorry, these orange dots are the earthquakes that took place. These are the actual data. And so the blue over predicts, perhaps the green under predicts. And you can imagine that the best model would bound the seismicity almost perfectly. And so that's what you really want. And so what we're going to do here is we're going to try and develop a better model for this bounding behavior. So we're going to look at the geothermal stimulation at the Forge site. I think most of us are familiar with that. And then we'll also look at a CO2 EOR site in Farnsworth, Texas. So this is in the Texas Panhandle, and they've been injecting CO2 for I think I'm not quite sure how long they've been injecting CO2, a couple of years at least. And so the data for the forge simulation, this is just a histogram of the earthquakes given in time. And so the injection takes place in the red curve. And so it's a very short duration injection. It's only about a couple hours. And the maximum event that took place is towards the trailing end. It's even after the injection ceased. And then also the seismicity that we see for the CO2 EOR site is sort of more consistent, and it's over a much longer period of time. We also see these runaway rupture events where there are a lot of earthquakes that line up on a fault plane, which is potentially problematic for a large rupture. Luckily, that did not occur. The largest event took place during one of these runaway rupture events, and again, it's at the end of the time window, but it's not at the end of the injection. So the injection is still ongoing. So if we plot up those 4 literature models for these 2 formations, or these 2 sites, you can see that they do okay. They do well. So the early time seismicity in the forge site is not well constrained. The statistical model does a really good job of constraining the maximum event in the forge site. The models do fairly well here, but there's a breakdown in the residual model, which we'll discuss in just a moment. And so like I said, we're really trying to just improve upon these models. So let's first look at this breakdown in the red curve, the residual in the CO2 EOR. So what is that? What's going on there? So if we look at this DM naught term, it has 2 terms associated with it, the injection term and the moment release term. Now, we're going to be taking the logarithm of that DM naught term. So if the moment release is bigger than the injection term, then that means that this is going to be a negative value, and you can't take the log of a negative value. So that's why it broke down. And so what that means graphically is at some point, the moment release becomes greater than the injected value. And so that causes a breakdown of the model. Now, some authors believe that this might be a good thing because it might indicate when runaway rupture is occurring. That's definitely a possibility. So we've tried 2 improvements to these models. So the first improvement is the dynamic b-value. So if you imagine, if you take the b-value of your Gutenberg-Richter relationship in time, it's going to change. So if you take it for the first event, or the first 10 events, it's going to be different than if you take it for all of the events. And so we let this change in time. So we just take that log linear fit of the data, and we let it vary in time. And then this is what it looks like. These are the data in time, so individual, like actually linear time. And then if you look at it in terms of index, because most of the events are all right here, if you look at it in index, then you see that it's steadily increasing because most of the events are small, so it causes a steeper slope. But then it becomes much shallower. The slope becomes shallower. The b-value becomes smaller when you have these larger events right here. And so that's the dynamic b-value. If we plug this into the models, we get something reasonable. It looks okay. It bounces seismicity somewhat, but it's not a clear improvement. So we tried a second thing, a dynamic seismic efficiency factor, which that scaled injection versus the moment where we saw the breakdown of the residual model before. So instead of letting that just be a constant scaling factor, we changed the scaling factor to always make the moment release and the scaled injection be equal. So this is now always equal during the duration of the injection. And now what we see, this is for the geothermal stimulation, we see that the dynamic seismic efficiency factor, the blue, rather than the previous model, is actually well improved. It's significantly better to use the blue model, the dynamic seismic efficiency factor, on the geothermal. And then you can also see that in the CO2 EOR, there's a trend of increasing magnitude with time of the seismicity, which is not captured by the static seismic efficiency model, but it is captured by the dynamic seismic efficiency model. And so we're actually pretty pleased with both of these results. And so now you can imagine that the best model, that's the question. Like the question you want to ask yourself is, what is the best model we can use? And I think ideally you would want to know very specific site-specific things about the physics, about which physical model represents what's actually happening in our site. Barring that, you might actually be able to use a composite model. So calculate all of the models and then use a misfit criterion in the last 50 earthquakes or however many earthquakes to determine what is the appropriate model at any given time. And so we did that calculation in sort of like a quasi real-time sense, which you see here. And you can see that this composite model bounds the seismicity better than any of the other previous models. And so just food for thought, really. It's just food for thought. Is this an appropriate way to use these models, or would you rather just use a consistent model based on what you believe the physics are? And I'm not sure what the answer is to that. Okay, so the summary of the maximum magnitude. So 2 additional models are tested and they perform well. Ultimately, a real-time adaptive model could inform operators, despite the differences in the operational brand. Oh, this is something I didn't really mention. So the two sites, the Forge site and the EOR site, are very different, shorter durations, longer durations, different fluids, all sorts of differences between the 2 sites. And despite that, the models work very well for both sites. It's actually remarkable in my mind. So now I'll give a brief summary of the talk. So we had the probabilistic hazard prediction section, which showed that probabilistic geomechanics can lead to an assessment of the hazard on faulting scenarios and tell us which faulting scenarios we need to look out for. Fault curvature. So these are so in this study we showed that the spatial relation of the spatial distribution of the hazard changes along the fault given different stresses and given different curvatures and orientations of the fault. The creep section, we saw that the change of this creep that takes place, this viscoelastic creep that takes place in the formations over geologic time, can give us an assessment of the stresses in the present day. And then finally, we saw in the MMAX prediction that we can create these models that bound the seismicity, that better bound the seismicity, and that improve our ability to predict what's going to happen with future injection. And so thank you all very much.
Thank you very much, Kevin. Very nice talk. Very captivating, very engaging. And now I open the floor for questions. You have some questions in the chat. If you could please read them aloud and then answer them, I would appreciate it. First from Brian.
Okay, 1 sec. I can't get can I stop sharing my screen? Is that okay?
Sure, of course.
Oh boy, sorry, technical difficulties. Okay, so Brian's question is the seismicity sparse or is the equipment sparse?
Yeah, that was when you were discussing. Thank you, Kevin. Again, I echo Sharzad's comments. Really terrific presentation and discussion that you've laid out. When you summarize the San Juan Basin seismicity, you mentioned that the seismicity is sparse, and it echoes an analysis from literally 20 years ago of the Aneth field in the Paradox Basin, one of your other sites, one of your sites in your presentation today, where the initial characterization of the site was very sparse seismicity, but then once all the geophones were installed, it's like, oh, there's over 100 events per day. Now they're between -1 and 1, but there are hypocenters events every day, all the time, and throughout the basin, although they were clustered along 2 faults. So it just kind of reminded me of that analysis, and just wanted to ask you about the context for "quote unquote" sparse seismicity or seismic events.
Yeah, so I mean, it's so my take on that is that the entire upper continental crust of the Earth, everywhere you have upper continental crust and even oceanic crust, you have seismicity, and it's fractal. It's a matter of, you know, it's a power law distribution where as you get to smaller magnitudes, you have more events, and you get to bigger magnitudes, you have fewer events. And so I think that, you know, that fractal nature, like the parameters of that curve are different based on where you are in either the oceanic or the upper continental crust. And so I think in some places in the upper continental crust, like San Andreas Fault area or Alaska, you have a different distribution of that fractal curve. And then in other areas, like for instance, the San Juan Basin, you have different parameters describing that curve, but the curve is essentially the same kind of thing. That's my take on that, Brian. Does that satisfactorily answer the question? I'm not sure.
Absolutely, it really does. Thanks so much. I know that if one were to leave geophone arrays, broadbands, whatever, installed over a longer term, I think I think that's probably not probably, I think you're absolutely correct. So yes, it's a lot of the data that we 20 years ago were collecting simply reflected where the equipment was present and not that fractal self-similar nature. So yeah, thanks for that context. Yes, I think you're sounds just right. Thank you.
Thank you, Brian.
Thank you.
Oh, go, Sharza.
Yeah, you can see them better probably. Amy has shared 2 of your papers. They were open access, so thank you, Amy, for sharing it with everyone. And then we have one from P. Rasumi. What is the role of stress perturbation due to temperature in geothermal environment? Perhaps locally it might affect stresses due to cool injection, but does the far field SH mean SH max change? Far field.
So yeah, so there's definitely going to be an impact of the temperature on the stress field, but it's not going to be, it's just going to be a localized impact where the actual temperature perturbation is taking place. So the far field stresses typically are assumed to be tectonic. I mean, there are other factors that play into that, of course, but largely due to the tectonics. And so so I think, you know, it's a matter of the resolution. So those far field stresses, meaning the SH min and the SH max that you experience at the injection site, will change, but the stresses acting on the perturbed area in terms of like the regional continental stresses should not be affected by the injection into a smaller region.
So the far field is constant, but locally it has to redistribute itself to get to that constant again.
Exactly, yeah.
So Brian has another question here. Farnsworth injection, almost 15 years, but intense monitoring of that injection in just a few years, as Kevin suggests. So I guess
I think he was letting me know how long they've been injecting, because I stuttered on that. Is that right, Brian?
Oh, no. It was just a comment that Kevin was absolutely correct. It's only been monitored closely. This gets back to our geophone discussion a moment ago. It was only monitored closely for the past few years, as Kevin indicated. CO2 injection, now water injection began back in the 1950s, 1960s, but the CO2 injection didn't begin until almost about 15 years ago. And but the monitoring of it, really, that's the key factor here. Is it's only been a few years, as you indicated, Kevin. So all good.
That makes a lot of sense. That explains a lot of the things I've been seeing on that project.
Nice. Nice. And Pirasumi, folks, you can always unmute and speak up, elaborate on your question if it is not enough what we are reading and answering. Characterizing faults as curve sounds good, but what does dip slash strike mean for the curve fractures?
Oh, I think the idea is that, you know, a strike and a dip is inherently a description of a plane. That's a very good point. That inherently those are descriptions of planes. So what we did was we discretized that fault. So in each of the little regions we created, we assumed a plane in those regions. So we had a series of planes describing the curvature of the larger fault, but in each of those planes, especially to make the math work, we had to use a plane, and that's a good point. And then with the kriging, it's the same thing. It's you have a tangent plane. We used a tangent plane to the krieged surface, and that was our representation of that little tiny discretized point of, yeah. That's a great question.
That makes sense. Thank
Yeah,
you.
sorry, this is Prasad Umesh
Hi.
from Houston Baker Hughes. Thank you very much for both the questions. You answered quite well. So thank you very much.
Of course, no worries.
Thank you. And Shivesh has this question: in probabilistic hazard prediction, if we will include the variation of rock parameters by using reliability analysis along with probabilistic analysis, will that be beneficial for the model analysis? So basically, rock parameters, rock physical parameters, properties.
Yeah, I think so. I mean, it's all a matter of I'm not sure I fully understand this question. I need to preface this answer with that. But it's you know, the amount of granularity you can apply to the analysis usually helps, not always, but usually. So I think if you can incorporate, you know, more physics, more measurements, more data into the analysis, usually that helps. I mean, sometimes, like, you can imagine a sort of an end member case where you're trying to weigh how much this coffee can weighs, and you also take into account the intensity of the sun. I mean, that wouldn't help. So it depends on how you have to do it appropriately. But if you incorporate more physics, essentially, you should, so long as it's done appropriately, it should create a better model.
Only the analysis may become a little more expensive. And he can
True.
always
You're gonna have to apply for bigger grants.
Exactly. He's in the building, in our building, actually. His office is in our building. He can always stop by to elaborate on his question later.
Oh yeah, for sure. Because I'm not sure I fully understood that question. So yeah, please stop by.
Nice. And Neil Watson asks, do you think your model would be significantly enhanced by a better understanding of fault dip, strike, curvature, and other fault features through a balanced structural model?
Yes, the answer to that is yes. I think the biggest problem in everything that I presented today is just the uncertainty in understanding where, how big, what orientation, what curvature, any of these faults, like the geometric parameters of these faults. It's so uncertain. We have seismic data, we have geologic inference, we have we have wells, we have a few things that can get at it, but the better you can understand the presence, location, size, curvature, all those geometrical parameters of the faults, that helps tremendously.
Very nice. And Pirasumi is just thanking you for your answer on the role of temperature on locally and far field stresses. Okay, any other questions for Kevin, folks? He's my neighbor, so I can always ask my questions. And if no more questions, we are gonna give Kevin a virtual clap, praise, lots of questions coming from the chat, and thank you, sorry, not questions. Thank yous are coming, and thank you so much, Kevin, for accepting my invitation, and thank you for helping always with ARMA Future Leader lecture series. We will see you all in 2 weeks for another great lecture by ARMA Future Leaders. Thank you.
Thank you. Thank you, Shahrazad. Thank you, everyone. This was fun. Thank you.
Thank you, Kevin. Bye-bye.